All right, and kind of as promised, this next question gets very gross. Suppose now that string 2 is embedded in a viscous medium such as molasses, which imposes a drag force proportional to the transverse speed, i.e., the change in force of drag is equal to negative gamma df dt times delta z for some change in length. All right, so A, derive the modified wave equation describing the motion of the string, and B, solve the equation assuming that the string vibrates at an incident frequency omega. That is, look for solutions of the form tilde f of z of t is equal to e to the negative I omega t capital F tilde of z. Okay, so we're trying to split up the time and spatial components. C, show that the waves are attenuated. That is, their amplitude decreases with increasing z. So that's going to be very important later on as well. And what we want to do is find a characteristic penetration distance at which the amplitude is 1 over e of the original value in terms of gamma, t, mu, and omega. D, if the wave of amplitude ai, phase delta I equals 0, and frequency omega is incident from the left, string 1, find the reflected wave's amplitude and phase. Okay, long question, but we just saw how to deal with this on the last question, so we'll kind of zoom through some of the setup stuff. But let's consider some of forces to start. So if we're looking at some minute change of force from the tension in the string, we just have T delta squared F over dz squared delta z. Okay. Similarly, if we consider the force of drag, we see what that is. And then Newton's law tells us that the change in force is equal to ma, where mu is the linear mass density. So mass density times the delta z for however long it is gives us the total mass, and we have acceleration as d squared f dt squared. So we're good there. Now, in order to sum these two together, we have to have the tension, we have to have the drag, and then we have to set that equal to the ma side of the equation. So now our wave equation, instead of being a t d squared f over dz squared equals d squared f over dt squared, we have to include that drag force on the dt side. So that's our modified wave equation. That was pretty easy to find, but again, it goes back to the Newtonian laws. Now the rest is the fun part of dealing with this resultant wave equation. So as stated, if we're looking for solutions of the form tilde f z of t is equal to e to the I omega t capital F tilde z, then the wave equation reads, well, we just have to plug this in. Notice that the e to the negative I omega t cancels in every term. And so we just have to simplify after the derivatives are evaluated. And then as we solve this thing, we see that we have the capital F of z is a second order term, which we can solve accordingly. If we make the substitution for that coefficient on the F of z term be a negative k squared, k tilde squared. And we know that the solution has a form of f tilde z is equal to a tilde e to the I k tilde z plus b tilde e to the I k tilde z. And since the tilde is representative of a real part, we need k tilde, so we resolve it into real and imaginary parts. And when we do that, we see that we go for k tilde equal k plus I kappa, which gives us, if we square it, just distribute it through, we see that we have the k squared plus 2I k kappa minus kappa squared is equal to omega over t times mu omega plus I gamma. Okay, that all comes from the fact that we had that we solved to put the differential equation in standard form. Nothing really new there. The imaginary part, again, we see is 2k kappa is equal to omega t times gamma. So kappa is equal to omega gamma over 2kt, square that through, and we see that we get a kappa squared term. The real part is k squared minus kappa squared, hence the need to have the kappa squared. So once we solve that and push the kappa squared in, we see that we get a k squared term here, which so to solve this for k squared, we now have to use the quadratic formula. Since we have a kappa to the fourth, kappa squared, all that stuff, thanks to the fact that, k to the fourth, thanks to kappa squared having a 1 over k squared term in it. Once we simplify the algebra there, let's go ahead and plug it in. Again, the quadratic form is ax squared plus bx plus c equals 0. And this gives us two solutions, so I'll let you see how we do that. What we do to try to facilitate easier algebra is highlighted in the red. Multiply by a factor of 1 in the form of omega mu over omega mu. And then simplify it through as much as we can. Pull that out, and let's go ahead and keep simplifying. Now we're left with a simplified form of mu omega squared over 2t bracket 1 plus or minus the square root of 1 times, or 1 plus parentheses gamma over mu omega squared. But k is real, so k squared has to be positive. So we need the plus sign. Okay, and this makes sense because that if we took 1 minus that square root, which is greater than 1, and then we took the square root of k, since we have k squared here, that would give us an imaginary term. So again, this is why we go with the plus sign, and we'll just rattle off through and solve for k. Once we do that, we get this nasty expression here. A lot of algebra. I told you the section's gross. So now that we have k, we can quickly solve for kappa as well. Plug that in. Thus, what we see here is that the form of the equation, f tilde of z is equal to a e to the I k plus I kappa z plus b e to the negative I k plus I kappa z. Once we separate those into real and imaginary parts, where we have a e to the negative kappa z, e to the I k z plus b to the kappa z, e to the negative I k z. Again, we'll see this repeatedly throughout this chapter as well. But the b term gives an exponentially increasing function, which we don't want. I assume the waves are propagating in the positive z direction, so we say that b is equal to 0. Therefore, the solution here is tilde f of z of t is equal to tilde a e to the negative kappa z e to the I kappa z minus omega t. Whew. Okay, so even through all that, what we see here is that this is a general form solution, and the only things that really change are the kappa and the k's for whatever situation we have. And so let's continue on. So the wave is attenuated by a factor of e to the negative kz, which becomes 1 over e when z is equal to 1 over kappa. Okay, so as you see there, we just set e to the negative kappa z equal to e to the negative 1. So negative kappa z equals negative 1. Easy enough to solve that through. So z is equal to negative 1 over negative kappa, hence how we get this. And we saw what kappa was equal to, so no big deal there. And that is the characteristic penetration depth. So for part D, this is the same as before, except K2 goes to K plus I kappa. So if we plug that in, we see the ratios come about, and we again, with the squares, we have to take the complex conjugates. And as you see here, we get AR is equal to the square root of K1 minus K squared plus kappa squared over K1 plus K squared plus kappa squared times A1. When really all we really want is the amplitude, or the ratio of the amplitude rather, where K1 is equal to omega over V1, and then we know that V1 is equal to the square root of mu1 over T, with K kappa are defined in B. So if we do this thing with the complex exponential again, we said we have e to the I phi, solve that through, tangent of phi gives us what we're looking for, which is delta R is equal to tan inverse of everything once it's simplified, which is negative 2 K1 kappa over kappa 1, or K1 squared minus K minus kappa 2, or kappa squared. Blah. As you see, we got a lot of the same stuff. And yeah, that's all for this one. But that complex exponential comes in handy quite a bit. The forms that we need for tangent are quick to solve. You just got to be very careful with how we deal with them and simplify them through. Other than that, we should be good to go.